Hello, I am Hasbi Sevinc and I will represent my thesis project step length estimation using sensor fusion. In this work, we propose a method that will help indoor positioning. We estimate step length of walking person. In that way, if we know initial position of the person and if we know direction of the person, we will be able to obtain person location while he or she is walking by estimating step length. Although GPS is a commonly used navigation system, it doesn't work properly for indoors because of the signal losses. There are some studies to solve this problem. Pedestrian depth reckoning (PDR) algorithm, which is a localization technique that uses inertial sensors to estimate pedestrians' location. PDR uses inertial measurement unit (IMU) sensors like accelerometer, gyroscope, and magnetometer. Since this technique is cost efficient and requires low computation, it's extensively used. However, PDR systems suffer from integration drift problem like all inertial navigation systems. The small errors in the sensor measurements cumulatively increase over time and cause larger errors in the positioning. To solving drifting problem, Modar and his friends combined Wi-Fi fingerprints and IMU sensors. They estimated step length of walking person position by using IMU sensors and they uses Wi-Fi signals to position of the person. However, their system requires predefined knowledge about location of Wi-Fi routers in the building. Renoiden and his friends combined two IMU sensors. One of them is mounted to foot of the person and other IMU sensor is handheld. They also applied fast Fourier transform to eliminate interference signals caused by drift problem. In this study, we are proposing a step length estimation system using sensor fusion. We combine textile-based capacitive sensors, IMU sensors of smartphone and SmartCane. Textile-based capacitive sensors are manufactured by adding insulator silicon dielectric layer between two flexible, high-conductive knitted fabrics. As the fabric stretches, the silicon layer becomes thinner, which allows conductive surfaces to approach each other. Changing the distance between conductive surfaces causes the capacitance to alter. In this project, we attach these sensors to person's knees to measure joint angle changes while walking. Figure shows the electrical circuit to measure capacitive values of textile-based capacitive sensors. A microcontroller that is Atmega 328 was used to read two different textile-based capacitive sensors which are attached to person knees. A regulated battery was used to provide required power to system. A Bluetooth module was used to transmit measured data. Smartphone was put in the right bucket of the subject to measure physical changes that occurred during walking using its IMU accelerometer, gyroscope, and magnetometer values. SmartCane's onboarded IMU sensors are also used to measure physical changes during walking. Unlike the smartphone, the SmartCane also allows to measure the different dynamics of the walking movement as it contacts the ground. The SmartCane WeWALK developed for visually impaired people. It detects optical with its distance sensors and warns the user with vibration sensor. The data of all sensors, including textile-based sensors, are combined along with time information and they transmitted to a computer via Bluetooth. The figure shows attached sensors and their position on the body while collecting data. We applied signal processing methods to collect the data. First, we applied pre-processing methods to make data better for machine learning models. Then, we extracted features from the pre-processing signals and at the end, we used feature selection methods to reduce dimensions. Electrical systems can generate noise during their work. Therefore, the collected dataset was first smoothed with a low-pass filter. In addition, the values of this dataset were normalized between 0 and 1. In the step detection, in order to divide the gate dataset into steps, the local maximum and minimum points in the signals were detected. Each maximum point is marked as the midpoint of the step. The local minimum points on the right and left of the midpoint, it represents the start and end point of the step. Using this method, steps are segmented from the signals. For the machine learning model to work with high accuracy, the features to be extracted from the signal are great importance. From each detected steps, the following 13 features were extracted. They are minimum value, maximum value, mean value, variation, standard deviation, median, quarter interval, kurtosis, skewness, mean absolute deviation, value interval, and time interval, and mode. Quality of extracted features directly affect the performance and speed of the machine learning models. Therefore, it is necessary to eliminate features that have not significant influence on the model. In this study, we use principal component analysis (PCA) that provides dimension reduction using all data. During natural walking, step lengths do not always equal to 10, 20, 30 centimeters. Since they will not be equal to the labeled lengths, models should be trained with a regression approach instead of category-based methods in the step length calculation studies. We trained models with linear regression, support vector regression, k-nearest neighbor, and random forest algorithms. All signal processing and machine learning steps were done in the computer having 8 GB RAM and Intel Core i7. A track consisting of 20, 30, 40, 60 cm step lengths has been set up to collect sensor data. In this track, points to be taken are marked. We collect data of 5 different volunteers walking at normal speed on the track. The dataset containing 2,872 feature vectors were divided into 72%, 18%, and 10% as training, test, and validation dataset to prevent overfitting. R-square, mean squared error, root mean square, and mean absolute error metrics were used to evaluate performance of the regression models. R-square values close to 1 indicates that the developed model is compatible with the dataset. The values of mean squared error, root mean square, and mean absolute error values are inversely proportional to the performance of the model. When the regression models adapt to the dataset, the values of these metrics are expected to approach to zero. In this section, the performance values of the models are represented. PCA method has been applied to reduce the size of the extracted features. This way, the performance and operating speed of the system are increased by reducing the complexity. Table shows regression model scores. According to these results, the best fitted method on the test dataset is k-nearest neighbor regression method with 0.945 R-squared score. In this work, we combine textile-based capacitive sensor, smartphone, and SmartCane device to predict step length of a walking person. While the textile-based capacitive sensor worn on the knee provide information about the person's step and movement. Accelerometer, gyroscope, and magnetometer sensors on the SmartCane and the smartphone also provide information about the person's movement direction and speed. We performed walking tests and collected sensor measurements to create a new dataset. We use this dataset to estimate step length of a walking person. In this work, we get 0.945 R-squared score by using k-near-neighbor regression method. This research is a step forward towards ensuring that people with visual impairments move safely indoors using the obtained results in this study. In the future, orientation information will be integrated with the step size to enable safe indoors navigations. Thank you for listening.